Hi, I'm Jeff Groh, and this is Calculus 1, Exam 3 Review. On question 1a, I ask you to classify the critical points of the following function: 3x cubed minus 4x plus 6. The first step is to find the critical points. So we'll calculate the derivative, set it equal to 0, and solve for x. Moving the 4 over, dividing by 9, and taking a square root, you get x is plus or minus 2/3. Don't forget the plus or minus. Instead of solving by moving the 4 over and dividing by the 9 and taking a square root, you could have factored 9x squared minus 4 as a difference of squares, and that works just as well. Now that we have the critical points, we can use any method we'd like. I haven't told you to use either the first or second derivative test, so you may use either one. We'll plot, in this particular case, the critical points on the number line, and then evaluate the first derivative at points in each of the resulting 3 intervals. Something less than negative 2/3 might be negative 1. Negative 1 squared is 1 times 9 is 9, minus 4 is a positive 5. At 0 we get a negative 4, and at 1 we get again positive 5. So you can see it's going up until it gets here and then down. We have a relative max. Down until it gets here and then up. We have a relative min. We'll state our answers as follows. F has a relative max at x equals negative 2/3, and F has a relative min at x equals positive 2/3. On problem 1, part B, we'll classify the critical points for 4x cubed minus 45x squared plus 150x plus 25. Again, the first step is to find the critical points. So we'll calculate the derivative, set it equal to 0, and solve for x. We'll have 12x squared minus 90x plus 150. The factors of 12 are, say, 4 and 3. 4 does not divide evenly into 90, so you can at best take out a 2 from that 4. All 3 are divisible by 3, which means we can factor out both a 2 and a 3, or in other words, a 6 from each of these coefficients. We have 6 times the quantity 2x squared. Let's see, we're taking out a 6 from here. That leaves what, 15? And taking out a 6 from 150, 6 goes into 15 twice with a remainder of 3, and 6 goes into 30 5 times. We now need to factor the quadratic. Both will be minus. We'll have a 2x and an x. Factors of 25 are 5 and 5. This will give us minus 10, and minus 5 is minus 15. So the critical points are x equals 5/2 and x equals 5. Plotting these on a number line, remember, don't clutter your number line with hash marks. Use only the critical points or in other problems, points not in the domain. Evaluating the derivative at, say, 0, we get negative times negative is positive. At 3, 2 times 3 is 6. This is positive and negative. We get a negative, and if x is big enough, both of these are positive. So we get a local max followed by a local min. I want you to communicate these results to me in words. F has a local max at x equals 5 halves. F has a local min at x equals 5. And again, you may say relative instead of local, or local instead of relative. On problem 1, part C, and I really have to be honest, I'm not likely to give you parts A, B, and C on the actual exam. I'm just giving you extra problems to work in preparation for the exam. On this problem, we're given f of x equals 3x to the fourth minus 20x cubed plus 18x squared plus 108x plus 21. First step is, of course, to find the critical points. So we'll calculate the derivative, set it equal to 0, and solve for x. That gives us 12x cubed minus 60x squared plus 36x plus 108. Let's see, 12 goes into the first, second, and third coefficient. Does 12 go evenly into 108? Yeah, it goes in there 9 times. So we'll factor a 12 out. And now we need to find the roots of this cubic. Using Descartes' rule of signs, we go from positive to negative, negative to positive, and then positive to positive. There are 2 sign changes. That means there are at most 2 positive roots, 2 or 0. They disappear in conjugate pairs to go complex. That means there must be, since there are 3 roots, using the fundamental theorem of algebra, there has to be at least 1 negative root. Using the rational root theorem, the possible factors of 9 are 1, 3, and 9. So we'll take plus or minus these factors divided by the leading coefficient to get the possible rational roots. Using synthetic division, we can determine what those roots are pretty quickly. Let's see, 1 doesn't work. You can tell 1 doesn't work because you get 9, 12, 13 minus 5. That's not going to work. I'm not going to give you 0. Will negative 1 work? Let's try negative 1. And you can just see by inspection pretty much that it will. Multiply and add. Multiply and add. Multiply and add. And because we get 0, we actually have a root at x equals negative 1. So x equals negative 1 will be a critical point. We also know that this polynomial factors as x plus 1 times, I'll put a dot, x squared minus 6x plus 9. The quadratic factors as a perfect square. 12 times x plus 1 times x minus 3 quantity squared. And that gives us critical points, negative 1 and 3. Negative 1 is a critical point of multiplicity 1, and 3 has multiplicity 2. Again, using the first derivative test, the only critical points are negative 1 and 3. And we'll see what happens at, say, -2. Notice that the x minus 3 is squared, so this factor will always be positive. If we're at -2, we'll get a negative, and the slope there will be negative. Let's try 0 next. There we'll have a positive, and then if we plug in 4, positive again. So 3 is neither a max nor a min, but at -1 we have a relative min. F has a relative min at x equals -1, and x equals 3 is nothing. On problem 2, I ask you to find the absolute extrema of the function x cubed minus 12x on the closed and bounded interval -3 to 10. This function is continuous on a closed and bounded interval by the extreme value theorem. It must achieve both its absolute max and its absolute min on this interval. The extrema, absolute extrema, must occur either at an endpoint or at a critical point. So first, we'll find the critical points. Factoring a 3 out, we see that the critical points are plus or minus 2. We don't need to evaluate the derivative to find intervals of increasing or decreasing. All we have to do is evaluate the original function at the endpoints and at the critical points. All right, plugging in 2 cubed is 8. 8 minus 24 is -16. So at 2, we get -16. This function is odd, so you have to get the opposite sign at -2, which you can check independently. At -3, we get -3 cubed, which is -27, plus 36 for a total of 9. At 10, we get 1000 minus 120. What is that? 880. It's clear we have the absolute max here at 10, and the absolute min at 2, having a value of -16. I'll permit you to get away with not expressing these in words, but by affixing these labels here. On problem 3a, I ask you to find the intervals on which the given function is increasing and the intervals on which it is decreasing. The function in question is x cubed plus 3x squared minus 9x plus 1. We'll start by calculating the derivative. Factoring a 3 out, we then factor the quadratic. Make sure that you can factor the quadratic, or at least, we're solving for the critical points, at least you should be able to use the quadratic formula to find the critical points. Once we have the critical points, we'll plot the number line, and remember, don't clutter your number line with hash marks. Use only the critical points or points not in the domain. At -4, we'll have a negative and a negative, giving us a positive. At 0, we get a positive and a negative. It's going down there. At 2, everybody's positive, and so This function is increasing. Now keep in mind we can include the endpoints if we wish, and I won't mark you wrong if you leave them off, since your homework software doesn't count you off by leaving the endpoints off. But negative infinity to negative 3, union 1 to infinity, and it's decreasing from negative 3 to 1. Again, you may use rounded parentheses on the endpoints, though that is a bit vague. On problem 3b, again, there probably will be fewer problems than on the actual exam. The function is 9x to the 4th minus 32x cubed plus 24x squared plus 54. We calculate the derivative and set it equal to 0 to solve for the critical points. We have 36x cubed minus 96x squared plus 48x. What can we factor out? Looks like the factors of 36 are 4 and 9, but 9 does not go into 96. So it looks like the best you might be able to pull out is, say, a 12. How many times does 12 go into 96? 8 times. We can also pull out a factor of x. So what's left over? 3x squared minus 8x plus 4. We now need to figure out the roots of the quadratic. (3x) and x, both minus. What are the factors of 4? Looks like 2 and 2. That'll give us negative 6 minus 2 is negative 8. The critical points are x equals 0, 2/3, and 2. We'll plot the number line. You don't need to be too careful about spacing these, and don't include any other hash marks. Plotting one point that's negative here, we'll get a negative, 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 3 negatives. If we plot something like 0.1 or maybe 1/2, positive, negative, negative, we get 2 negatives, so it's positive. Plotting 1, this becomes positive, positive, negative. We get a negative there, and plotting 3, we get positive, positive, positive. Everybody's positive. It follows then that we're increasing from 0 to 2/3, union, from 2 to infinity. We are decreasing from minus infinity to 0, union, 2/3 to 2. On problem 4, I ask you specifically to use the second derivative test to classify the critical points of the given function. In fact, I don't even bother giving you the function, I give you the derivative. Read the problem carefully, make sure you're not writing down f when it's really f prime. This is going to be 6x squared minus 30x minus 84. And we're using the second derivative test. 6 clearly goes into 30. It also goes into 84. It goes into 8 once with the remainder of 2. And then 6 goes into 24, 4 times? So we should factor a 6 out of this first. Now, the factors of 14 are 2 and 7. We'll keep factoring then. X, 7, 2. The 7 gets the minus, whereas the 2 gets the plus. Our critical points are -2 and 7. We'll plot these. We won't plot these on the number line because we're not using the first derivative test. Instead, we need to calculate the second derivative. That's going to be 12x minus 30. If you wish to use smaller numbers, I suppose you could factor a 6 out. Evaluating at -2, we'll have 2 times -2 is -4 minus 5 is -9 times 6 is -54. In particular, that's negative, which means you're concave down at -2, and that means at the critical point where you have slope 0, you have a relative max. Now we'll try 7. 2 times 7 is 14, minus 5 is 9, times 6 is positive 54. And in particular, we have a positive concavity, it's concave up, and so at the place where the slope is 0, we have a relative min. On problem 5, I ask you to determine the intervals on which the given function is concave up and where it is concave down. The function itself is 1/6 x to the 4th minus 9x squared minus 1. I also ask you to state the x coordinates of any inflection points. Normally inflection points have both an x and y coordinate, and you state it as a point. In this case, I'm not asking you to do the extra work of finding the y value, but rather just state the x coordinates of any inflection points. We begin with calculating the first derivative. You see that we get 2/3 x cubed minus 18x. And then we calculate the second derivative, which is 2x squared minus 18, which will factor as 2 times x squared minus 9. X squared minus 9 is a difference of squares, and it factors as a difference of squares. We see that the possible inflection points occur at x equals -3 and x equals 3. Plotting a number line for f double prime, we'll plot -3 and 3. If we plug in something like -4, we'll get negative, or concave up on this region. At 0, we get a negative second derivative, so it's concave down there. And at a place like 4, we get a positive. So we have concave up on -infinity to -3, and from 3 to infinity, concave down, -3 to 3, and the inflection points are at x equals -3 and 3. On problem 6, I ask you to sketch the graph f of x equals x squared plus 2x plus 3 divided by x minus 2. Now, on this problem, I also ask you to show any x-intercepts, y-intercepts, or asymptotes. So intercepts and asymptotes. I know that in class we had 4 steps for graphing these. The first step was intercepts, second step was asymptotes, the third step was the first derivative information, and the fourth step was the second derivative information. I'm not asking you to do all 4 steps here, just the first 2. I'm reasoning that I'm asking you to give the other first derivative info and second derivative info on other problems. So I won't ask you to do that here. Just give me intercepts, asymptotes, and the graph. On intercepts, part A is the x-intercepts. You find the x-intercepts by setting y equal to 0. The only way a fraction can equal 0 is if the numerator is 0. Well, it turns out this numerator can never equal 0. You can try any number of ways to prove this. One simple way to prove that is to complete the square. You would like to add plus 1, so you'll split off a 1 from the 3. This gives you x plus 1 squared plus 2, which means that this function can't be any smaller than 2 because this is non-negative. This will have no solutions, so there are none. On part B, we need the y-intercepts. To find the y-intercepts, you set x equal to 0. Plugging in 0, we get negative 3/2. So far, the picture looks like this. At negative 3/2, the curve crosses the y-axis, and there's no other information. On part 2, we look at the asymptotes. The vertical asymptotes are usually obvious by inspection. In this case, x equals 2. There are no horizontal asymptotes since the degree on top is greater than the degree on the bottom. For a rational function like this, remember what a rational function is? A function that talks and makes sense? No, a ratio of a polynomial divided by a polynomial. A rational function will only have a horizontal asymptote if the degree of the polynomial in the numerator is less than or equal to the degree of the polynomial in the denominator. If the degree on the bottom is higher, it's automatically y equals 0 as a horizontal asymptote. If the degrees are the same, you take the ratio of the leading coefficients. In this case, we have instead a slant or oblique asymptote since the degree in the numerator is exactly 1 higher than the degree in the denominator. You can find this by either long division or synthetic division. The root of the denominator is 2. Bring the 1 down, multiply, and add. You can discard the remainder, and we get y equals x plus 4. As the slant asymptote. So it's going to cross, say, at 4 with a slope of 1. Extend these way up. We're going to need that extra room. It's now easy to figure out what happens. We have an intercept here, and we must also remember the important principle that the graph must be asymptotic to the asymptotes. Remember that basic principle. Duh. Yes, the graph has to be asymptotic to the asymptotes. That's what they're there for, folks. So this has to go over here and down here. Now, there are 2 possibilities over here. It can either go up like this and be asymptotic to the asymptotes, or it can go like this and be asymptotic to the asymptotes. But it can't do this because if it did, it would cross the axis. and there are no x-intercepts. So the graph must in fact do something like this. This is all I'm asking for. On problem 7, I ask you to find all numbers c between 2 and 8 that satisfy the mean value theorem for the function f of x equals x plus 3 divided by x. You might remember the mean value theorem tells you that provided the function is sufficiently smooth, namely continuous on the closed interval 2 to 8 and differentiable on the open interval 2 to 8, then there has to be some point c where the derivative at c is equal to the slope of the tangent, slope of the secant line. So in this case, let's calculate the derivative. F prime of x is going to be 1 minus 3 over x squared. So we're looking for a point c where 1 minus 3 over c squared is equal to, let's see, f of 8. 8. In the numerator, we'll have 8 plus 3/8 minus 2 plus 3 halves divided by 6. We have then 8 minus 2 is 6 plus 3/8 minus, let's convert to eighths here, 12/8. That's going to be 6 minus 9/8 over 6. We can simplify this by dividing 6 into each of the terms in the numerator. We'll have 1 minus 9 over 6 times 8. I'm being a little cagey there because I want to reduce this fraction first. We'll have 1 minus 3 over 16. You can see then that we can cancel the 1 off of each side. We'll have a negative we can cancel from each side after that, and a 3 that we can cancel, and c squared is going to be 16. It follows then that c is plus or minus 4, but only one of those is in the resulting interval. So c equals 4 is the answer. Problem 8 has multiple parts. In this problem, we're asking you to calculate limits. And in particular, we're going to be using L'Hopital's rule at many junctures. On the first problem, we're taking the limit as x goes to 0 of sine x minus x divided by x cubed. If you just evaluated x equals 0, sine of 0 is 0, minus 0, the numerator is 0, the denominator is also 0. This is a 0 over 0 case, and that is a L'Hopital's rule case. So applying L'Hopital's rule, we'll take the limit as x goes to 0, and please show your work on the exam. The derivative of the numerator is cosine of x, and then minus 1, the derivative of the denominator is 3x squared. Evaluating at 0 again, cosine of 0 is 1, we get to 0 over 0 again, so we apply L'Hopital's rule a second time. I'm writing limit as x goes to 0 of negative sine of x over 6x. Now, you may either apply L'Hopital's rule again, or use the fact that sine x over x goes to 1 to declare that the answer is negative 1/6. On 8b, we have the limit as x goes to infinity of, let's say, 3x squared plus 7x plus 2 over 4x squared minus 3x minus 3. I'll be terribly disappointed if you have to show any work. Since the degrees are the same, you get 3/4. If we altered this a little bit and wrote the limit as x goes to infinity of 3x cubed plus 7x plus 2 over 4x squared minus 3x minus 3, I'd also be disappointed if you didn't just write plus infinity. On part C, we have the limit as x goes to 3 from the right of 1 over x minus 3. You should be able to immediately see that you get plus infinity. On part D, we're taking the limit as x goes to infinity of cosine x over x. The numerator is bounded between -1 and 1, so we can use the squeeze theorem to prove that since this is bounded and the bottom is blowing up, the whole thing is driven to 0. On part E, we're taking the limit as x goes to 0 of e to the x minus 1 minus x divided by x squared. This is clearly a L'Hopital's rule problem. So this will be the limit as x goes to 0 of e to the x minus 1 over 2x, which is again a L'Hopital's rule problem. So we'll take the limit as x goes to 0 of e to the x over 2 and get 1/2. On part F, we're taking the limit as x goes to 0 of cosine of x minus 1 plus x squared over 2, and we are dividing by x to the 4th power. Again, a L'Hopital's rule problem. This gives us the limit as x goes to 0 of negative sine x plus x over 4x cubed. We again have a L'Hopital's rule problem. Taking the derivative, we get negative cosine of x minus 1 over 12x squared, which is again a L'Hopital's rule problem. We'll have sine x over 24x. Sine x over x tends to 1, so the answer, we're halfway done. On problem 9, I ask you to prove that this function x cubed plus 6x plus 3 equals 0 has exactly one solution on the interval from -3 to 0. You might remember from the lecture that these problems have two parts, existence and uniqueness. So in our proof, we'll first address existence. I want you to state your answers in complete sentences where possible. Something like what we're about to write. First, note that f is continuous on the interval -3 to 0 since it is a polynomial. Second, let's evaluate the function at the endpoints. -3 times 6 is -18, plus 3 is -15, plus -27 is -42, the salient point being that you get a negative value. F of 0 is 3, and that is positive. This means that 0 is intermediate to -42 and 3. By the intermediate value theorem, there must in fact exist c between -3 and 0 such that f of c equals 0. We've proven existence using the intermediate value theorem. You must state that you are using the intermediate value theorem. The next part of the proof is uniqueness. In this part, we do a kind of reductio ad absurdum method, a proof by contradiction. Suppose there are two solutions, x1 and x2. Note that f is differentiable on the interval -3 to 0, since it is a polynomial. We have now checked the hypotheses of Rolle's theorem. By Rolle's theorem, there exists c between -3 and 0 such that the slope at c is 0. The function goes through points x1 and x2 where it crosses the axis, so there has to be some place where the slope is 0. But let's take a look at that derivative. The derivative is in fact 3x squared plus 6, and that can never be 0, and that's a contradiction. That means there can't be 2 or more. There must be only 1. We deduce that there is at most one solution. Combining the two parts, existence and uniqueness, there is exactly one solution. On problem 10, I ask you to find the dimensions of the largest right circular cylinder that can be inscribed in a sphere of radius a. So let's find the dimensions of the largest can that can be inscribed in a sphere of radius a. The dimensions are the radius and the height. I'm going to write half the height for this part here. You can see that we've done this strategically so that we have a right triangle. We can now write down a relation, r squared plus 1/2 the height squared is the radius of the sphere squared. In other words, r squared plus 1/4 h squared equals a squared. This is a constraint on r, h, and a being a fixed constant, r and h being the variables in the problem. We want the largest volume. The volume of the can, by the theorem of Pappus, is pi r squared h. You can take the area of the top, pi r squared, and multiply it by the distance h to find the volume of the resulting figure. We're trying to maximize the volume subject to the constraint given by the Pythagorean theorem. The problem with maximizing this volume is that we have two independent variables, r and h, but we can eliminate one of those using our equation here. Let's eliminate r squared. R squared is a squared minus 1/4 h squared, so that the volume is pi times h times a squared minus 1/4 h squared. We now have a single variable, independent variable, that we can then take the derivative, set it equal to 0, and solve for h. We'll distribute the h first. When we do, we'll have pi a squared minus pi times 3 h squared over 4. We can divide the pi off, that won't matter, and then solve for h. H squared is going to be 4/3 a squared, so that we get h, which must be positive, so we'll take a positive square root, 2 over the square root of 3 times a, and a is positive as well. So h is 2 root 3 over 3a. We have the dimensions for h, the height. It only remains to find r, but we can get that by substituting over here. R squared is a squared minus 1/4 h squared. H squared was 4/3 a squared. And so r squared is 2/3 a squared. One of them minus a third of them is 2/3 of them. Taking a square root, we'll get the square root of 2/3 times a. And for the purposes of the exam, I won't require that you rationalize denominators. So that's it. On problem 11, I ask you to find the dimensions of the largest open top. So it has a side and a bottom, but no top. Open top, right circular cylindrical can that is to be made of material weighing 2 grams per square centimeter. If the can is to have a volume of 512 cubic centimeters. If you haven't figured it out, the density 2 grams per square centimeter for the side and bottom material is a red herring. We need to minimize the surface area. The surface area is, well, we have the bottom, pi r squared. We'll define r and h. Plus the area on the side, which is the circumference, 2 pi r times h. Using the theorem of Pappus to find the area on the side. This has 2 independent variables, r and h. Fortunately, the volume is pi r squared h, and that gives us a constraint that we can use to eliminate one of the independent variables. S is the objective function, and we're trying to minimize that in order to minimize the total weight. The volume formula is our constraint. It allows us to eliminate one of the independent variables. So if we solve for h, we'll have 512 divided by pi r squared for h. The surface area formula is then pi r squared plus 2 pi r times 512 divided by pi r squared. Pi will cancel in the second term. 2 times 512. 2 times 512 is 1024. And we can cancel an r. To optimize in this problem, we calculate the derivative, set it equal to 0, and solve for r in this case. We have 2 pi r minus 1024 divided by r squared. Moving this term over, we have 1024 over r squared is equal to 2 pi r. We can divide the 2, get our 512 back, multiply an r squared onto both sides and divide by pi. We'll have r cubed is 512 divided by pi. 512, by the way, is 2 to the power 9. 1024 is 2 to the power 10. Everyone needs to know 1024. is 2 to the power 10. If we've knocked a 2 off of that, it's 2 to the power 9. You can see that r is going to be the cube root. We'll have 2 to the power 3, which is 8, divided by the cube root of pi. That's r. We substitute into the formula for h to find h. Substituting, we have this 512, which is 2 to the power 9, divided by pi r squared, which is 64, over the cube root of pi squared. We can simplify this somewhat. 64 is 2 to the power 6, and 512 is 2 to the power 9. We can subtract exponents and get 2 to the power 3, or 8, over pi is the cube root of pi cubed. If we cancel 2 of those factors with 1, we end up with the cube root of pi for h, and that's the other part of our solution. I probably won't give you a couple constrained optimization problems on the actual exam. You just need to practice. Constrained optimization is a common area where students have difficulty. The only way to overcome that is to work problems. So I gave you a couple on the practice exam. On problem 12, I say that from a position 300 feet from the launch site of a model rocket, you measure the angle of inclination at apogee to be 42 degrees. You estimate that your angle measurement could be off by up to 2 degrees because you must have an amazing angle measurement device that measures these things on the fly. How high do you estimate the rocket has gone? And 2, how many feet could your estimate be off? So on part 1, we ask how high. Let's define our variable h. An important step in solving applied problems is to define a variable name for what you're solving for. H divided by 300 would be opposite over adjacent. That's the tangent of 42 degrees. It follows then that h is 300 times the tangent of 42 degrees. On the exam, just put a box around that. On problem 2, I want you to estimate how far off that height computation can be. So we're going to first write this as h equals 300 times the tangent of theta, leaving the angle theta, the thing that has error, variable. It follows then that dh is going to be 300 times the secant squared of theta times d theta, using our formula for differentials. We'll plug everything in since we're only looking for error here. If I'm asking for relative error, you have to find dh over h. If I'm asking for percent error, it's dh over h all times 100%. On this particular problem, I'm asking you to find the error. So dh is going to be 300 times the secant squared of 42 degrees times the error in theta, which is 2 degrees, and that must be converted to radians. So you'll write 2 pi over 180, and this will be your answer. You'll be happy to know that we are now on the last page of the practice exam. On problem 13a, I ask you to calculate the indefinite integral of 3x squared plus 4x minus 9. I should give you 3 points if you can do this right, and negative 1,000,000 points if you get it wrong. This should be pretty easy. We'll use the power rule for antiderivatives down the line. This one, first term is x cubed. The second term is 2x squared, and then 9x. and plus c. Please do not forget plus c on these indefinite integrals. On part B, I'm asking you to tell me the indefinite integral of e to the x dx. On all of these, you write an antiderivative plus an arbitrary constant c. The antiderivative of e to the x is e to the x, and then plus c. On part C, I want the integral of 1 over x dx. You need to know that that's the log of the absolute value of x plus c. Don't be cheap with me. Don't leave off the absolute values. On part D, I have the integral of cosecant squared x dx. This is minus cotangent of x plus c. I could give you any one or all of the derivatives of the trig functions, and you need to find then how to backtrack those. And finally, the integral of 1 over x squared plus 1 dx, which is arctan of x plus c. That's the one. That's the one I want you to know. Finally, on problem 14, I ask you to perform 2 iterations of Newton's method using x0 equals 1 to approximate a solution to the equation x squared minus 2 equals 0. So of course we will set f of x to be x squared minus 2. The formula for Newton's method was xn plus 1 equals xn minus f of xn over f prime at xn. In this case, that's xn minus the quantity xn squared minus 2 divided by 2xn. We can simplify this if we wish. We'll have xn minus 1/2 xn plus 1 over xn. The two will cancel when we distribute and divide this into 2 pieces. This gives us xn divided by 2 plus 1 over xn. We are now ready to perform those 2 iterations. We have a formula for xn plus 1 here. Using 0 here, we'll have x0, which is 1 divided by 2 plus 1 over 1. It's 1.5 or 3/2. That's one of our 2 answers. x2 is going to be 3/2 divided by 2, which is 3/4, plus 1 over 3/2, which is 2/3. That's what? 9 plus 8 is 17/12. I won't mind if on the exam you leave it like this.